Imagine launching a spacecraft 45 years ago and having it still explore regions it was never originally meant to reach, operating far beyond its scheduled lifespan. That's the astonishing reality of NASA's Voyager 1 spacecraft, the most distant human-made object in existence. This bold mission, launched in 1977, has redefined space exploration by pushing the boundaries of human achievement and technological endurance. What's even more fascinating is that this spacecraft, now billions of miles from its starting point, continues to beam data back to Earth using technology that predates the cassette player. Yet, despite its outdated systems, Voyager 1 has just made a discovery that has captivated the global scientific community, shaking long-held assumptions and sparking intense curiosity across the world. What exactly is this astonishing find in the far reaches of space, and what does it mean for humanity on Earth? To understand this, we must go back to a pivotal moment in the history of space exploration, when two of NASA's most iconic missions took off, ushering in a new era thanks to the brilliant mind of Gary Flandreau at NASA's Jet Propulsion Laboratory. A precise and elegant route was mapped out that would allow a probe to visit the giant planets Jupiter, Saturn, Uranus, and Neptune, armed with nothing more than a pencil and the basic engineering tools of his time. Flandreau discovered something extraordinary in the late 1970s and early 1980s. The four gas giants would align in a rare cosmic configuration, creating what was essentially a celestial necklace linking Earth to the outer solar system. This alignment made it possible for a spacecraft to gain speed using gravity assists from each planet, a clever trick where the craft slingshots around a planet and borrow some of its orbital energy as though being tugged forward by an invisible hand. This gravitational boost would cut down the time needed to reach Neptune from 30 years to just 12. There was, however, a critical catch. This alignment only occurred once every 176 years. Faced with such a rare and fleeting opportunity, NASA moved swiftly, launching two nearly identical spacecraft, Voyager 1 and Voyager 2, just 15 days apart in the summer of 1977, to take full advantage of this cosmic shortcut. What no one anticipated back then was that these twin spacecraft would go on to shatter every record in the history of space missions more than 45 years after their launches. Voyager 1 and Voyager 2 are still operational, beaming back invaluable data daily from the farthest edges of our solar system. These probes have become the most distant human-made objects ever sent into space, traveling far beyond what their original designers imagined. An incredible feat, especially when you remember that their initial mission was only supposed to last 4 years. But these two explorers, true pioneers of interstellar space, were far from finished from the very start. They began delivering remarkable surprises, transforming our understanding of the outer solar system as they embarked on their epic journeys. The Voyager spacecraft gave humanity its first detailed close-up views of Jupiter and Saturn's moons, revealing astonishingly active and dynamic worlds. Who could have predicted, for instance, the discovery of active volcanoes on Jupiter's moon Io, or the complex ice fields of Saturn's moon Enceladus? These observations forever altered our perception of the solar system, showing that even distant frozen moons could harbor geological activity and perhaps even conditions suitable for life. Voyager 2 went on to become the first and so far only spacecraft to visit Uranus in 1986 and Neptune in 1989, revealing previously unseen details and surprising scientists with findings from regions never before explored. Now more than 14 billion kilometers from Earth, these Volkswagen Beetle-sized probes have defied expectations at every turn, expanding the frontiers of human knowledge with each passing day. The mission's innovations began even before it left Earth to achieve their remarkable trajectories. The Voyager spacecraft executed gravity assist maneuvers that had never been tried before, starting with a delicate slingshot past Venus en route to Mercury. This pioneering approach allowed the spacecraft to reach Jupiter, a journey requiring them to traverse 10 times the distance between Earth and Mercury, all while threading a path through the hazardous asteroid belt, a feat that had only been achieved by the Pioneer 10 and 11 missions before them. Despite the challenges, the Voyager probes carried on, powered by onboard computers with just 69 kilobits of memory, a minuscule fraction of the storage found on even the simplest modern smartphones. These computers had to manage the intricate and demanding tasks of deep space navigation, data collection, and communication, relying on their own onboard intelligence to handle the journey's enormous complexity. The data collected by the Voyager instruments were stored on track tape recorders before being transmitted back to Earth using a low-power 23W transmitter, equivalent to the energy consumption of a household light bulb. Each spacecraft was equipped with a 12T diameter high-gain antenna, allowing it to communicate with Earth across vast cosmic distances using light-speeded radio signals. However, as the spacecraft moved farther from Earth, the challenge of communication grew increasingly difficult. Every day the distance increased by 3 or 4 light seconds, meaning that by the time Voyager 2 was sending signals back, they were taking more than 18 hours to reach our planet. Complicating matters further was the rising tide of background noise on Earth. Interference from radios, televisions, cell phones, and countless other devices made the faint signals from the spacecraft ever harder to detect. Despite these mounting obstacles, the Voyager probes astonished astronomers and engineers by continuing to deliver groundbreaking discoveries. As they journeyed toward the edge of the solar system, they helped rewrite our understanding of the vast uncharted regions beyond the planets, including the mysterious Oort cloud, a vast halo of icy comet-like objects bound together by the sun's gravity and stretching halfway to the nearest star. Although the Voyager spacecraft have not yet entered the Oort cloud, they achieved a historic milestone when they crossed the helipause, the outer boundary where the solar wind's influence ends and interstellar space begins. Scientists had initially estimated that the helipause lay about 50 astronomical units AU from Earth, and so NASA decided to continue funding the Voyager mission as the probes approached this landmark. Yet crossing into interstellar space did not unfold exactly as scientists had expected. Researchers had predicted that upon crossing the helipause, the spacecraft would detect a sharp increase in cosmic rays, high-energy particles traveling at nearly the speed of light, launched by powerful cosmic events such as supernovae. Normally, the sun's magnetic bubble, known as the heliosphere, deflects most of these energetic intruders, shielding the solar system from harm. As the Voyager probes moved past this barrier, scientists also anticipated changes in the local magnetic field, since the interstellar magnetic field, shaped by the influence of nearby stars, was thought to be oriented quite differently from the solar magnetic field inside the heliosphere. But as the probes ventured farther, they did not record any immediate or dramatic shifts in the magnetic environment. Leaving scientists puzzled, the big moment came on August 25, 2012, when Voyager 1 officially crossed the helipause and transmitted groundbreaking data back to Earth. It confirmed the expected increase in plasma density, a hallmark of interstellar space, but curiously it detected no significant change in the surrounding magnetic field's direction. This finding was unexpected and has continued to challenge scientists' understanding of the boundary between the solar system and the interstellar medium, after all, moving from a region dominated by the sun's magnetic influence to one governed by the collective forces of neighboring stars, should have produced a clear and measurable shift, yet the data told a more complex story, one that continues to intrigue researchers as they analyze the spacecraft's reports from this distant and little understood region of space. In many ways, the Voyager mission has become a living testament to human ingenuity, determination, and curiosity even today. With its antiquated systems and dwindling power supply, Voyager 1 continues to explore uncharted territory, sending back whispers from a realm no human has ever seen. Its incredible journey reminds us that exploration is not just about the places we visit, but about the persistence and creativity we bring to every challenge we face. As Voyager 1 sails onward into the great cosmic sea, it carries not only the dreams of the people who built it, but the hopes of an entire species longing to understand its place in the vastness of the universe. Do you want me to include the details about the golden record and its message to alien civilizations? Voyager 1's plunge into interstellar space not only marked a triumph of human engineering, but also opened a door to a cosmic environment we had only theorized about before. As it crossed the helipause, scientists anticipated that they would observe dramatic shifts, particularly in the magnetic field orientation, yet the magnetic data defied expectations. Instead of encountering a distinctly different magnetic alignment, Voyager 1 reported that the magnetic field outside the heliosphere remained largely consistent with what it had measured inside. This puzzled researchers, suggesting that the boundary between our sun's sphere of influence and the broader interstellar medium might be more complex and blended than the clean-cut division they had modeled. Rather than a sharp line, the helipause seemed to be more like a turbulent, mixing region where solar winds and interstellar particles intermingled, blurring the edges between solar and interstellar domains. This insight prompted a reevaluation of existing models and revealed how much we still don't know about the frontier regions of our solar neighborhood. While Voyager 1 led the way into this new realm, Voyager 2 followed, crossing into interstellar space in November 2018. Despite being its twin, Voyager 2 carried additional scientific instruments that Voyager 1 no longer had functioning, providing even more valuable data about this uncharted environment. As both spacecraft pressed outward, they measured plasma density, magnetic fields, particle flux, and cosmic rays, painting an unprecedented picture of the interstellar medium's characteristics. Perhaps one of the most exciting discoveries came when Voyager 2 detected subtle waves or disturbances in the plasma it passed through, ripples likely caused by solar outbursts many months earlier, traveling outward and shaking the interstellar medium. This observation highlighted that even as far as the spacecraft had traveled, the sun's influence continued to reach across unimaginable distances, sending shock waves that still resonated in the thin plasma of interstellar space. The data streaming back to Earth from these ancient machines isn't just a scientific curiosity, it's a testament to endurance and ingenuity. Voyager 1 and 2 are operating with mere traces of power, rationed carefully by mission engineers, who must decide which instruments to prioritize as the available energy dwindles each year. Originally powered by 3 radioisotope thermoelectric generators (RTGs), the spacecraft's electrical output has been steadily declining for decades. This has forced the mission team to shut down non-essential systems, including heaters, leaving some instruments exposed to frigid space temperatures they were never designed to endure, and yet defying the odds these instruments have continued to function sometimes beyond their expected tolerances, allowing the Voyagers to extend their mission years beyond any realistic projections. Each decision about what to power and what to sacrifice reflects a delicate balancing act, one that the mission team handles with extraordinary care to prolong the life of these invaluable emissaries. Among the most intriguing aspects of the Voyager missions is the golden record, a 12 inches gold-plated copper disc attached to each spacecraft, carrying sounds and images intended to represent life on Earth. This record, the brainchild of a team led by astronomer Carl Schon, contains greetings in 55 languages, a selection of world music, natural sounds like thunder and birdsong, and 115 images depicting the diversity of life and culture on Earth. While its chances of being encountered by another civilization are astronomically slim, the golden record stands as a symbolic gesture, a time capsule of humanity launched into the cosmos. It reminds us that the Voyager probes are not just scientific instruments but also cultural ambassadors, carrying a message across the vast emptiness between the stars that might someday outlast all traces of human civilization on Earth. The discovery that has shaken the scientific community recently relates to something Voyager 1 detected as it traversed the interstellar medium, an unusual and persistent hum, a faint plasma wave that suggests the interstellar medium is not as quiet and still as once assumed. This discovery points to a background of low-level vibrations, a kind of cosmic hiss that could reveal new insights about the density and movement of particles in the space between stars. Such findings challenge long-held assumptions and force scientists to rethink what interstellar space really is. Far from being an empty vacuum, it appears to be a dynamic environment shaped by complex interactions among stellar winds, magnetic fields, and plasma flows. For Earth-based researchers, every bit of data the Voyager's return adds another piece to this cosmic puzzle, enhancing our understanding of the galaxy and even informing future plans for interstellar exploration. Beyond the scientific revelations, the Voyager story resonates on a profoundly human level. These spacecraft were launched in an era when computing power was limited, when long-distance space communication was still an emerging field, and when the idea of a probe surviving for nearly half a century was almost unthinkable. They embody a kind of optimism and ambition that characterized the early space age, a determination to reach further and understand more despite the challenges. Each signal they send back is a triumph of persistence, a tiny thread connecting us to machines we built decades ago, now sailing through a realm no human has ever visited. The engineers and scientists working on the Voyager project today often speak of the deep emotional bond they feel with these probes, a sense of responsibility, respect, and even affection for these enduring travelers. Looking ahead, the future of the Voyager missions is bounded by their dwindling power supplies. At some point in the coming years, the RTGs will no longer produce enough electricity to run any instruments, and the spacecraft will fall silent. They will continue on their trajectories, of course, drifting through interstellar space, but without a voice, without the ability to call home yet. Even in this final phase, they will remain part of the human story, silent witnesses to the universe, carrying the golden record and the legacy of Earth into the cosmos. Scientists estimate that in about 40,000 years, Voyager 1 will pass within 1.6 light-years of the star 445, while Voyager 2 will pass near Ross 248 in about the same time frame, though the chances of an encounter are virtually nil. The thought of these ancient machines continuing their journeys through the galaxy, perhaps long after humanity has faded carries a kind of poetic beauty that transcends pure science. The Voyager's achievements remind us that exploration is not just about immediate returns or practical outcomes. It is also about curiosity, wonder,